Hello everyone, we're about to start the next session. So we have here Kemal Okoyum. He's going to be speaking about profiling Python with eBPF. Profiling is certainly one of the most challenging parts I had with Python in the last 20 years when I've been coding with the programming language. So I really can't wait to hear what you have to share with us. Thank you very much and welcome.
Hello, everyone. So let's start with some questions. Does anyone here knows anything about eBPF? Okay, quite a lot of people. Have you ever used profiling? Wow, nice. Do you know anything about Python? Great, everyone, that's nice. Okay, first, who I am. I'm not Prometheus, but I'm a Prometheus maintainer. Do you know or use Prometheus? Okay, that's also great. So I'm a maintainer of Prometheus. I'm also a maintainer of Thanos, and recently I'm a maintainer of a Parca project. These are all open source projects, and they are all focused on observability. And I think I know something about observability, so today I will tell you about that. So let's start always with why. Why do we need profiling? It's either for some performance optimization. This graph can be anything generic. This could be CPU, this could be memory, and you see some spikes, and you would try to understand what's going on actually on those spikes. Or this could be something about an incident. This graph is specifically for a kill that your process, and you don't know what that happened at that certain point, and you would like to know about what function or which component of your process actually allocates the memory in that particular moment. So some of you already know that there exists some profiling solution in Python. This is not an exhaustive list, but most of the libraries or projects that you see in here, you actually need to instrument your code. So either you need to import a library or you need to specifically write some code and then start profiling your application, Python application. But this is not always the ideal case because you would sometimes you don't have access to code itself, and sometimes you would like to do this from outside. So how do you do that? This is where eBPF actually comes into place and helps us. So eBPF it's originally for networking applications. It's called Berkeley Packet Filtering, but now eBPF totally something else. It's basically an event-based system where you can hook into some events that Linux kernel issues, and then you can just run code as a reaction to those events. There is a runtime, there's a virtual machine inside, and there's a verifier. Before you load your program, that verifier needs to check your program that it doesn't do anything harmful, like infinite loops, whatnot, in the kernel space. Then compiler kicks in and compile your provided code, and you actually run those code against any events that you issue. That's the one fancy part of the solution. So then it comes another subsystem of Linux, which is super cool, is the perf event. You can have the perf subsystem, and from the perf subsystem you can have you can hook into various parts of your stack, and you can run code against these events. And in this particular talk, we are going to talk about the CPU events, but you don't need to use only the CPU events necessarily. You can do this for the I/O events, you can do this for the memory allocation. Practically anything that you see in here, you can run hook into that event and run a code piece to that. So what makes perf events special? It's actually performance monitoring units. These are very efficiently implemented units in the Linux kernel, so that they keep track of the cycles, and then you can actually take measurements and you can react to those measurements. So that's why eBPF plus perf events is actually its faster than the other solutions that we have in the basically ecosystem. Because with the Linux, you can already have some syscalls. You can just like hook into that interrupts and do all these things that I'm going to tell you in a minute in the user space. But the most of the things we do is using the PMUs, and again, because of PMUs are efficient and eBPF code's also efficient and runs in the kernel space, this gives us a bit of a headroom for the performance. So we are not the only ones that actually implemented that. This is quite a journey. I don't remember when is the first time that it's actually introduced the PyPerf code inside the Linux kernel. You can check out, these are actual links, and I'm going to share the slides, and you can see basically the Git commits against that. There's also, there's a set of tools called BCC tools in the eBPF space, and there's also another implementation of PyPerf in there. But what is the downside of all these tooling? These are, first, they are dated. They don't cover all the recent changes in the Python runtime itself, and they are just one-off tools. So I'm going to show you some cool things that you can actually do profiling in the production run itself in a continuous manner, which we call continuous profiling. We're going to come to that in a minute. So to make these tools work, you need to just like wrap your Python interpreter run with these tools and then collect your profiles. So that gets us to the Parca project. It's an open source project. It's a continuous profiling project. Using eBPF and perf events, we can run your profiling workloads directly in production, and there is no runtime, nearly none of the runtime overhead in this approach. There's a tiny bit, but it's really negligible. So how does the Parca eBPF agent actually work? Similar things that I mentioned previously. We hook into perf events. We have some unwinder programs that actually unwinds the stack, which I will tell you about, and we then keep a track of like what happens in the CPU for that stack, and then we aggregate those information and put in an eBPF map, which are the special data structures that you talk between kernel and the user space. And then we read that data, we convert that some open profiling formats and push that in a server side where we can just aggregate and visualize that and let the users actually make sense of their programs. So this is how that whole thing actually works. There are a lot of details, but this talk is like not actually about the internals of Parca, but we are doing like a lot of cool stuff to make the stack collection and symbolization very efficient. And then the end result is a UI like this. In a continuous timeline, you can see that like what's going on your CPU for each process, and we collect a lot of metadata and enrich those information for you, and so that you can query, compare, and see how you can improve your program. And the agent is kind of super cool because you can just install any host machine, and any process that you have on that machine, we can just collect data and send to the server, and you can see that in the UI. This doesn't necessarily, like, it's not scoped to the Python itself, but like it does a lot of cool stuff with the Python as well. So this is not a Python stack, but we will see some examples. But this is some, I think this is a Go one, but like you can see that the stacks are easily can get really deep. So what is the stack unwinding? This is the next critical thing that we need to talk about, because like the whole, like what makes profiling challenging, especially from the Python side, is actually to be able to unwind the stack. So when a program gets executed, probably you all heard these in your like start of your education. There are specific structures when the process actually allocating the memory, which is one is stack, and one is heap, and the stack is actually tracks the execution of the program. And whenever you call a function, you open a frame and you push change the states of your registers, and then you keep adding everything to the stack. And when one of the functions that returns from the leaf, you just like go back and return the data to your user. So I might be oversimplified that, but it's a diagram just to show you how it looked like. But the end result, when you unwind the stack and aggregate all these function addresses, you get something like that. It's just the machine addresses, and now you need to find a way to translate those machine addresses to the human readable format. So all these parts for the native code, so anything that actually runs on your CPU. So that brings us actually the next step. So this is a state where we didn't implement the Python unwinder for Parca. And you can actually, this is an interactive one. So you can see anything that gets from like your kernel. There's a start thread. This is coming from libc. And all these green things that you see, these are coming from the Python interpreter itself, because Python interpreter is written in C and it's compiled and that directly gets executed to on the CPU, but probably this is not useful for you, right? You are Python developers. You actually want to see what's happening in the Python process itself, not the underlying infrastructure. That being said, we also know that like most of the Python applications also rely on the C bits and the native code bits, and like it could be calling some C function here and there. Then when that happens, these are actually gets like super important, right? For example, PyTorch, it's very popular nowadays in the machine learning workload, but it's actually funneling everything into a native code. And when it's like when you want to see what's going on in the native code, Parca actually can do that as well. And we do that in a very, very efficient way. Like you don't need to have, there's the whole concept of frame pointers, and that actually helps us to unwind the stack. We just gave another talk in the observability room, like why frame pointers are cool. But you don't have to have, you need to have the frame pointers itself, because there's also another facility with the debug information. You can unwind the stack. So Parca, it actually utilizes that. This is important because most of the packages that you can find on any of the Linux distribution, you wouldn't find frame pointers. But with the dwarf information, you can actually unwind the stack and you can see all these calls. So, but we want more, right? We want to see the Python code. So how we actually do that? So this is where it comes to where we unwind the stack virtually. With virtual stack, we mean that anything that gets executed in the Python interpreter, we need to find those stacks and put those things in our flame graphs, so we can see that like where is the problematic areas in our Python code itself. So everything starts with opening the Python runtime and reading the code. This is the huge structure. Like if you know the Python internals, like it's long. Like there are a lot of comments, but it's not the easiest code to read, and it's not the easiest code to reason about. Let's focus on like what is the important bits, right? We care about the interpreter state, and from that bit, we want to capture what's going on each thread, right? It comes from the interpreter state, and then we try to find the Py state itself. The PyThread structure, it's like a linked list, so that whenever you have multiple threads running in an interpreter, you can just like, you need to traverse the whole, this linked list, and for each thread, you actually need to do that. But also you need to find out which thread actually captures the GIL and global interpreter lock, so that that's the one actually executing the code. So from finding all those information from thread state, you check the thread state. Oh, yeah, it's another like pages long C code that we need to reason about. It's not the easiest thing, but this is how reverse engineering kind of works. And again, I extracted the important bits. So from that thread state, we need to find what is the current frame is actually executing so that we can unwind from there, right? That's actually the same thing that we are doing with the native stack, but rather than checking some registries and reading raw memory addresses, we are actually checking the Python internals itself. So from the interpreter frame, it's easy, like whatever we need, it's here. So all the information we need is here. We have the pointers to the previous stack, and we can actually do the same thing. So I'm going to speed things up. Yeah, we have the map, we know the source code, but where do we actually start? When we have an object file from the Python interpreter, we first need to find where does all these structs are actually live. So we check the entry point of a Python interpreter. We see that it's linked against a libpython. And we go and check the names for one of these structs symbols, and we actually see that there are some offsets that allocated that. But this is just from the binary. We don't know what these addresses mean when a process started. So this happens because this is just one of the reasons. But when you get a binary and run the process out of that binary, there's some address randomization, and all those addresses needs to be translated to that. So how do we do that? We just run a Python interpreter and check what's going on in the process. This is basically memory mappings, and it shows you where actually Linux maps the certain objects, and we check out the libpython, grab the base address, and from the addresses that we find from the symbol or dwarf information, we actually find where the structs are actually allocated in the memory. We are looking for those. And from that, now we need to read that data, right? So here comes the GDB. GDB is an amazing debugging tool. And we jump into the process and started to poke around. We define a macro and to calculate the offsets of a struct, which reads from the dwarf information. You say that, okay, give me this struct and this field, and it gives you the offset of that. Since we already have the start address of the memory, we just calculate the next address and read the data from that. But as you can see, this is very manual labor. We cannot do this for each and every Python version or implementation out there. So we do this with another project ahead of time. We use Rust bindgen for that, which was super convenient because PySpy was using that. We just grabbed some offsets and generated all these things for a couple of versions. But we are also working on a dwarf-based reader, which is more scalable. You just grab any binaries, read the debug information, and calculate all the offsets. From those offsets, we generate this struct, which we synced over the kernel space. It's like a map, where to find the fields and everything. And the nice part that the whole things that we are working on, it's going to be deprecated soon because Python... This is life of a software engineer when you do reverse engineering. So that something super cool happened with in the Python main branch. Now they have this debug offset data structure where they generate all the offsets and put that in just the beginning of the Py runtime. We just can grab the address and just read the first chunk of the thing. Oh, we got the offset. We don't need to do this ahead of time things right now. So it's going to be, this is already merged, and it's going to be released with the Python 3.13. It's also huge, lots of stuff that you need to find out. Okay, actual unwinding stack. So these are where the eBPFs comes from. We did all the magic, we got the offsets, we put that thing into interpreter info structure and put that in an eBPF map so that eBPF program can read in the kernel. And this C code is in the kernel itself. We check something and get the interpreter info. This is the user space code where we actually calculate all the addresses and send and put to the eBPF map itself. And from that, we also grab this offset data that we calculated. We just do check some versions and find the runtime version of that particular Python interpreter, read the offsets, and from that offsets, we calculate that. But again, 3.13, this will be futile. So then we try to read data from the thread state, find those structures and read the pointers and try to find out where to go from there. 5 minutes left. I need to be super quick. Okay. So we try to find the initial pointer for the virtual frames. This is how we do it. And then from that, we start walking the stack. The key points here is just from the previous code that you can see. We actually put just line 13, put something into a state to the frame pointer, and we then read that frame pointer from another eBPF program. And from that pointer, we basically find the offset of the frame object where the code points to, read that row address with some BPF helper code. And from that, we read the symbol because like the addresses that we saw, that they don't mean anything to us. We are humans and we need some human readable data. And from that, to be efficient, because we keep seeing the same stack traces, we just like hash it and put that symbol somewhere so that if we see that, we don't need to send that same symbol to the user space because it's costly. And then we also encode the line number because symbols just represents a class, then a function, and then there's a line number in that function that is different. This API also recently stabilized in the Python, so for the old Python versions, this line number could be wrong, but after 3.10, it's actually it should be accurate. And then we encode that as well and send it to the user space. This is the reading the symbol parts. Like the code is like super complicated. I just highlighted the GDP outputs because it's like easier to read. So you read this nested structures and find the actual type name, then the file name, then the name of the object code and the first line in that function, and encode that as a symbol so that it means something for the humans. And voila, now we finally have Python unwinded stack. But as you can see, there are lots of things happening, and most of the things are interpreters, and it doesn't make any sense. But we have this cool UI. You can actually, these are like color coded. You can, from the color code, you can actually highlight like what's going on in the interpreter, what happens to the libc, libpython. You can see everything. But again, we want to focus on the Python bits, right? You can just filter out the Python code and see that it's recursively calling and calculating some Fibonacci numbers. Apparently, it's inefficient, so you need to optimize this. You can just tell by like depthness of the stack. Okay, you don't need to know the details of how to read the flame graph. But good thing for you, we also have a blog post for that. Like you can check it out. So I guess we are nearly out of time. So we support a couple of interpreters like 2.7, we still support that. So if you happen to have that. We support everything until 3.11. We are working on the 3.12 because 3.12 changes where actually the thread state also stored, which is the thread local storage. We are working on the facilities to read the state from the thread local storage. It shouldn't take more than a couple of weeks to be that support actually landed. And 3.13 will be there, so we don't need to do this again, basically, for the next versions of the Python. So everything you can see, please try, install, and give us a feedback. There's this QR code. It's a GitHub discussion. You can just engage with us and report bugs, and we can try to help you to profile and optimize your Python workloads. All the things that you see here, there's also a blog post if you want to catch up. You can check the company's blog post. And also, we find the unwinding bits super cool because it's a niche thing that we do. And if you, especially if you have an application that funnels everything to the native code, this will be super useful. Thank you for listening.
Thank you very much, Kemal. I'm afraid we're quite tight on the schedule, but please feel free to reach out to him with any questions.
Yeah.
And thank you very much.
Thank you.